The grid is one of humankind's most impressive feats of engineering. Nevertheless, it has some key limitations. One limitation is a lack of electricity storage. Our work models how an emerging grid energy storage technology called a Vanadium Redox flow battery would operate on the power grid. Because today's grid has essentially no electricity storage capacity, the power flowing into the grid from generators must continuously and precisely match the power flowing out of the grid to electricity customers. Any mismatch between power supply and demand could lead to a system-wide blackout, cutting off power to millions of people. Today, the grid operator balances the grid by signaling a fleet of power plants to quickly ramp up or down to match electricity supply with demand in real time. When power plants rapidly change their power output to keep the grid in balance, they deviate from their most efficient operating point, increasing fuel use and emissions. Modern battery technologies could provide a better way to match electricity supply with demand in real time. Because batteries can alternately charge and discharge without releasing emissions or suffering major efficiency losses, using them for grid balancing could save energy, improve air quality, and reduce greenhouse gas emissions. Furthermore, because batteries use fast electrochemical reactions to store energy, they can keep electric supply and demand in balance, even with large amounts of intermittent renewable energy on the grid. The goal of our study was to determine when batteries used for grid balancing might become cost competitive with power plants. To answer this question, we performed a model-based economic analysis of a vanadium redox flow battery participating in Texas's wholesale electricity market. Texas is a useful case study because it is the only state that operates its own power grid, administered by the Electric Reliability Council of Texas. Texas's grid is small enough to model while still being large enough to matter. Like a traditional battery, a vanadium redox flow battery stores energy in the electrochemical potential difference between two materials, which make up the negative and positive sides of the battery. In a flow battery, the energy storage materials are dissolved in large tanks of chemical solution, making flow batteries modular and highly scalable. Flow batteries last for 10 or more years and can be charged and discharged over 10,000 times before they wear out. We used published experimental data to develop a dynamic model for a vanadium redox flow battery. Then, we used our model with publicly available electricity market price data to show its value for frequency regulation service, the technical term for balancing grid supply and demand. We implemented a decision-making program with the model to optimize when the battery offers its power to the grid operator, mimicking how a battery owner would actually operate their system. Our model shows that a vanadium redox flow battery could be a cost-competitive solution for grid balancing if its cost is below $1,500 per kilowatt of rated battery power. Because vanadium flow batteries are still an emerging technology, their precise cost is uncertain right now. Studies estimate the cost of a system designed for frequency regulation is about $1,500 to $1,600 per kilowatt of rated power, similar to the cost of a new power plant. Thus, our results suggest that large-scale flow batteries are nearly a cost-competitive technology for balancing electricity supply and demand. Despite our findings, there are still a number of technical and non-technical challenges to wider use of grid energy storage. Conventional electricity markets and policies weren't designed to integrate devices that can both produce and absorb electric energy. Furthermore, many energy storage technologies are relatively untested and still in the demonstration stage. Nevertheless, if the cost of grid energy storage falls significantly, it could take on a larger role on the power grid. This work was sponsored by Pecan Street, Inc. of Austin, Texas, as part of their ongoing Smart Grid Demonstration Project, which is part of the American Recovery and Reinvestment Act Smart Grid Demonstration Program administered by the U.S. Department of Energy.